we need to talk about something the space agencies aren't saying out loud. Right now, in the dead of space between Mars and Jupiter, there's an object moving toward us that has astronomers breaking their own rules about what's possible. Its name is 3I/Atlas, and 5 days ago, on January 7th, 2026, the Hubble Space Telescope captured something that shouldn't exist, according to every law of physics we've written about comets in the last 400 years. I'm looking at the image right now, high resolution, undeniable. There's a jet of material shooting out of this thing, 400,000 kilometers long, that's the distance from Earth to the Moon, and it's pointing directly at the sun, not away from it, toward it, against the solar wind, against radiation pressure, against everything that should be pushing it back into the darkness. This isn't bending the rules, this is rewriting them in a language we don't speak yet. Every comet we've ever seen obeys a simple law. Heat from the sun causes ice to sublimate into gas. That gas gets pushed away by solar radiation and the solar wind. The tail always points away from the sun. Always. It's not a suggestion, it's physics. Pressure from starlight, streams of charged particles, they work together like cosmic wind blowing dust off a dirty windshield. The debris goes backward. That's how it works. That's how it's always worked. Until now. 3I/Atlas is doing the impossible. It's firing a coherent beam of material straight into the teeth of forces that should scatter it into the diffuse cloud within hours. And it's been doing this since at least July of last year. This isn't a fluke. This isn't a camera artifact. This is sustained, directional, and utterly unexplainable by natural processes. When astronomers first saw hints of this structure back in July, there was hope it might be an optical illusion, a trick of perspective based on our viewing angle from Earth. That hope died 5 days ago. The new Hubble data confirms it. The jet is real, it's stable, and it's dominant. Using specialized image processing, a technique called the Larsen-Secchi rotational gradient filter, researchers revealed that this sunward spike is actually part of a triple jet system. But while the other two jets are faint and diffuse, this one is tight, focused, and brilliant. It's not spraying, it's beaming. To maintain a structure 10 times longer than it is wide while plunging toward the inner solar system requires something we don't see in ice and rock. It requires velocity. It requires density. It requires containment. Natural sublimation doesn't do this. When ice turns to gas on a comet, it expands in all directions, or at worst in a broad cone before the solar wind sweeps it backward. What we're seeing here is controlled, narrow, directed. It looks less like evaporation and more like a nozzle. And then there's the brightness. At this distance from the sun, if the jet were made of standard cometary dust, the solar wind should be stripping away the smaller, lighter, more reflective particles, leaving only the heavy dark grains behind. The jet should be fading, diffusing, darkening. Instead, it's blazing, it's sharp, it's holding together. That means either the particles are impossibly massive and resistant to solar pressure, or they're being replenished at a rate that makes no sense for an object this size drifting through the void. Here's what makes this even worse. The jet has been visible for months. This isn't an outburst from a crack in the surface caused by thermal stress. This isn't a one-time eruption. This is a continuous operational state. The object is maintaining a precise orientation relative to the sun despite moving through space at tens of kilometers per second. Think about that. As it hurtles forward, as it rotates, as it tumbles through the vacuum, the jet stays locked on target, sunward, always sunward. In a natural scenario, a spinning comet nucleus sprays material in a spiral, like a broken sprinkler. To keep a jet pointing directly at the sun from a rotating body means the source of that jet has to be anchored to the subsolar point, the exact spot on the surface where the sun sits directly overhead. That requires either the object isn't rotating, which we know is false, or its rotation axis is aligned in a way so specific, so deliberate, that calling it coincidence starts to feel naive. And that's where the geometry comes in. Because when you map the wobble of this jet over time, when you reconstruct the spin axis of the nucleus, you don't find chaos, you find precision. The rotation axis of 3I/Atlas is aligned with the Sun to within 7 degrees. Let me say that again. The pole of this interstellar object is pointing almost directly at our star. That shouldn't happen. Spin axes are random. There's no rule that says a visitor from another star system has to orient itself toward the Sun. Tidal forces from the Sun aren't strong enough at these distances to have pulled the object into alignment during its brief passage through our neighborhood. It arrived this way. It came pre-aligned. But it gets stranger. Not only is the pole pointing at the Sun, the object's trajectory is also aligned with the ecliptic plane, the flat disk where Earth and the other planets orbit. Most interstellar objects, like Oumuamua or Borisov, come from random inclinations. They drop in from above or below, cutting through the solar system at steep angles like bullets through a paper target. 3I/Atlas is different. It's moving within the plane, sliding along the same orbital highway as the planets, like it knows where the lanes are. When you combine these two alignments, pole pointing at the Sun, trajectory flat with the ecliptic, you get a combined statistical probability of 1 in 10,000. 1 in 10,000. In science, when you see odds like that, you have two choices. Either you just witnessed an incredibly rare cosmic lottery win, or your assumption of randomness is wrong. If the alignment isn't random, if it's deliberate, then the object's orientation is constrained, controlled, coupled to its trajectory, or perhaps to the Sun itself. Debris doesn't do this. Interstellar junk doesn't aerodynamically stabilize itself in a vacuum. Tumbleweed doesn't grow fins. But 3I/ATLS is behaving like it has a fin, like it has control surfaces, like it's steering. The alignment of the rotation axis creates a permanent configuration. One hemisphere in eternal daylight, the other in eternal night. Maximum heating on one pole. If this were a natural comet, that constant solar bombardment might drive steady outgassing. But remember the jet. The jet is narrow. The jet is stable. If the pole is pointing at the Sun and the jet is firing from the pole, then the jet is acting like a thruster, applying force along the direction of travel. And if the object is elongated, which the light curve suggests it is, then any asymmetric outgassing should cause the spin to wobble, drift, accelerate. We call this the Yorp effect. But 3I/ATLS doesn't drift. It holds its stare. It keeps its nozzle locked on the Sun. This configuration essentially transforms the object into a stabilized platform. And stabilized platforms are not accidents of nature. They're engineered. So here's the question you need to answer for yourself. At what point does a stack of statistical improbabilities stop being a coincidence and start being evidence? We have a jet that defies physics. We have geometry that defies probability. How many impossible things do you need to see before the word impossible stops applying to natural origins? Because 3I/ATLS isn't just passing through. It's not drifting aimlessly back into the dark. It's heading somewhere specific. And the timing, the alignment, the trajectory, they all point to one destination. Jupiter, the king of planets. And it's going to arrive in exactly 9 weeks. On March 17, 2026, 3I/ATLS will pass within 53 million kilometers of Jupiter, threading through a region called the Hill Radius, the boundary where Jupiter's gravity begins to dominate over the Sun's. At that distance, Jupiter's escape velocity, the speed you need to break free and not become a moon, is only 2.2 kilometers per second. That's the threshold. Move slower than that relative to Jupiter, and you're captured. You orbit. You stay. 3I/ATLS is moving at 66 kilometers per second. It's moving 30 times too fast to be captured. For any piece of this object to remain in the Jovian system after the flyby, it would need to lose 64 kilometers of velocity instantly, in one moment. Natural fragmentation doesn't do that. When a comet breaks apart from thermal stress or rotational forces, the pieces drift away gently. They separate at walking speed, maybe jogging speed. In the most violent explosive outburst ever recorded, fragments might get kicked at 1 or 2 kilometers per second. We need 64. We need a fragment to slam on the brakes at interplanetary highway speeds and come to a near-complete stop relative to Jupiter. There is no known natural mechanism that can produce that kind of impulse without vaporizing the fragment in the process. The energy required is equivalent to a nuclear detonation focused entirely in one direction. Nature doesn't carry nukes. Nature doesn't have retro rockets. So if we see a new moon orbiting Jupiter after March 17th, if even one small object becomes gravitationally bound to the planet after this encounter, we are not looking at a natural event. We are looking at a maneuver, a precisely directed velocity change, an orbital insertion burn. And remember that anti-tail, that sunward jet we talked about at the beginning? It proved the object has a mechanism for directed thrust. It proved the object can maintain orientation. If that same mechanism is capable of a high-energy impulse, or if the jet we've been watching for months was actually a braking burn performed early to fine-tune this arrival, then the picture snaps into focus. This is the concept behind the Bracewell probe, a theoretical autonomous spacecraft sent to explore and monitor other star systems. A probe conducting a high-speed flyby might deploy a smaller subprobe, a scout, a relay, a package. To separate a subprobe at 66 kilometers per second and leave it behind in a stable orbit requires exactly the kind of impossible kick we're talking about. The smoking gun, the signature. If 3I/ATLS leaves the solar system intact, but Jupiter gains a new satellite, the laws of celestial mechanics tell us that satellite did not arrive by accident. It was placed, deliberately, with intent. The improbability of the alignment combined with the impossibility of natural capture physics creates a logical corner that the natural object hypothesis cannot escape. We are being forced to consider the alternative. The appearance of a new Jovian moon after this encounter would be extremely difficult, perhaps impossible, to reconcile with natural processes. It would represent a technological signature. Let me be clear about what that term means. A technological signature doesn't mean we have a photograph of rivets and antennas. It means we have data, observations, measurements that cannot be produced by the random background processes of the universe. The 400,000-kilometer jet pointing upstream against the solar wind? That's a signature. The 1 in 10,000 geometric alignment? That's a signature. A captured moon appearing at Jupiter in March would be the signature. And here's the thing. We're about to find out. March 2026 is not a distant hypothetical. It's 9 weeks away. And this time, we're ready. NASA has already adjusted observation schedules. The Juno spacecraft, which has been orbiting Jupiter since 2016, is still operational. It's aging, radiation damaged, running on borrowed time, but its instruments are active. Juno won't be close enough to 3I/ATLS to image surface details. Space is too vast for that. But it's perfectly positioned to detect the aftermath. If 3I/ATLS releases energy, if it fires a thruster to decelerate a payload, Juno's plasma wave instrument and magnetometers will see the disturbance ripple through Jupiter's magnetosphere. If a new object appears in orbit, Juno CAM can hunt for it in the weeks and months following the encounter. Ground-based telescopes will be watching too. Hubble, Keck, the Very Large Telescope. Every major observatory on Earth will have eyes on that region of space. For the first time in history, we're not scrambling to catch up with an interstellar visitor as it races away. We're waiting at the finish line. We're watching the door, and we're about to see what walks through it. Here's the verdict. If nothing happens, if 3I-Atlas passes Jupiter cleanly, stays intact, and vanishes back into interstellar space without leaving a trace, then we're left with a monumental mystery. An exotic comet that breaks every rule we thought we understood. We'll rewrite textbooks, we'll question our models. It will be strange, baffling, and ultimately natural. But if something stays behind, if something separates, decelerates, and settles into orbit around Jupiter, then everything changes. Humanity transitions from a species guessing about whether we're alone to a species studying an artifact left in our cosmic backyard. The impossible kick becomes proof of engineering, the alignments become proof of design, and we move from observers to participants in a story much larger than ourselves. We are 9 weeks away from one of the most consequential moments in the history of astronomy. Whether 3I-Atlas is a freak of nature or a messenger from the stars, it has already earned its place in the record books, but the final chapter hasn't been written yet. The data is still coming in, the encounter is still ahead, and the universe is about to give us an answer we didn't know we were ready to hear. March 17, 2026. Mark it, because on that day, we'll either witness the most bizarre natural phenomenon in solar system history, or we'll confirm what a growing number of scientists are quietly beginning to suspect, that we are not, and perhaps have never been, alone. Keep watching the sky. The clock is ticking.